Welcome to Makers 101. This is Lucas from Makers SoC. In this short video series, we will be taking a closer look at capacitors. To understand more about capacitors, we will be asking ourselves some of the following questions. The first question that we should ask ourselves is, what is a capacitor? A capacitor is a two-terminal electrical component which is widely used in electronic circuits. Now, you may be asking yourselves, what is all this terminology all about? Do not worry too much at this stage. We will be discovering more in subsequent slides. In short, a capacitor is like a temporary battery that can hold charges for a short period of time, depending on its capacitance. As shown in the diagram here, a capacitor can store electrical energy when it is connected to its charging circuit. And when it is disconnected from its charging circuit, it can dissipate that stored energy so that it can be used like a temporary battery. There are many different types of capacitors that are being used, but we will focus on the following four in this video. These are classified according to the type of material being used. The first one that we'll be taking a look at is the ceramic capacitors. It is the only non-polarized capacitor that we are looking at today. The second and third one belongs to the electrolytic family, which is the aluminum capacitor and the tantalum electrolytic capacitor. Lastly, we are going to take a look at the supercapacitor, which is also polarized. Now, before we dive right into those four capacitors that we're going to cover in today's video, let's understand how capacitors are made. The schematic symbol for a capacitor actually closely resembles how it's made. A capacitor is created out of two metal plates and an insulating material called a dielectric. The metal plates are placed very close to each other, in parallel, but the dielectric sits between them to make sure that they don't touch. The dielectric can be made out of all sorts of insulating materials such as paper, glass, rubber, ceramic, plastic, or anything that will impede the flow of current. While the plates, on the other hand, are made of conductive material such as aluminum, tantalum, silver, or other metals. They're each connected to a terminal wire, which is what eventually connects to the rest of the circuit. The capacitance of a capacitor is dependent on how it's constructed. More capacitance requires a larger capacitor. Plates with more overlapping surface area provides more capacitance, while more distance between the plates means less capacitance. The material of the dielectric even has an effect on how many farads a capacitor has. The total capacitance of a capacitor can be calculated with the flowing equation shown here. ER is the dielectric's relative permittivity, a constant value determined by the dielectric material. A is the amount of area the plates overlap each other, and D is the distance between the plates. With all these three variables known, you are able to calculate total capacitance of the capacitor. Now, after understanding how a capacitor is made, let's take a look at our very first capacitor today, the ceramic capacitor. The ceramic capacitor is the most commonly used and produced capacitor out there, and its name comes from the material from which the dielectric is made from. Ceramic capacitors are usually both physically and capacitance-wise small. It is hard to find a ceramic capacitor much larger than 10 microfarads. Some main advantages of ceramic capacitors includes its near-ideal capacitor rating, low cost, and non-polarized, meaning it does not have polarity. Now, let us take a closer look at the aluminum and tantalum electrolytic capacitor. The electrolytic capacitors are great because they can pack a lot of capacitance into a relatively small volume. If you need a capacitor in the range of 1 microfarad to 1 millifarad, you're most likely to find in an electrolytic form. They're especially well suited to high voltage applications because of their relatively high maximum voltage rating. The aluminum electrolytic capacitor, which is the most popular of the electrolytic family, usually look like little tin cans, with both leads extending from the bottom. Unfortunately, electrolytic capacitors are usually polarized, which means they have a positive pin, which is known as the anode, and a negative pin, which is known as the cathode. When voltage is applied into an electrolytic cap, the anode must be at a higher voltage than the cathode. The cathode of an electrolytic capacitor is usually marked with a negative sign and a colored strip on the case. The leg of the anode might also be slightly longer, as another indication over here. If voltage is applied in reverse of the electrolytic capacitor, they fail spectacularly by making a pop sound, and thereafter it will behave like a short circuit. These capacitors are also notorious for leakage, which allows small amount of currents in the order of nanoamperes to run through a dielectric from one terminal to the other. This makes electrolytic capacitor less than ideal for energy storage, which is unfortunate given their high capacity and voltage rating. Lastly, let's take a look at our final capacitor of the day, the supercapacitors. If you are looking for a capacitor made to store energy, look no further than the supercapacitors. These capacitors are uniquely designed to have very high capacitances in the range of farads. A 1 farad supercapacitor over here has high capacitance but has a small voltage rating of 5 volts. Notice that these capacitors are also polarized. While they can store a huge amount of charge, these capacitors can't deal with very high voltages. This 1 farad capacitor is only rated for 5 volts max. Any more voltage will destroy this capacitor. Supercapacitors are also commonly placed in series to achieve a high voltage rating while reducing total capacitance. The main application for supercapacitors is in storing and releasing energy, just like batteries, which are their main competition. While supercapacitors can't hold as much energy as an equally sized battery, they can release it much faster and they usually have a much longer lifespan. These are the electrical symbols that are associated with capacitors. On the left, we have the IEC standard, and on the right, we have the IEEE standard. Right now, we have taken a look and understood what a capacitor is. Let us now find out who invented the very first capacitor. Peter van Motionbroek was a Dutch scientist who was credited with the invention of the first capacitor in 1746, which is also known as the Leyden jar. He was also a professor who held positions in mathematics, philosophy, medicine, and astronomy. Let us now find out when do we use capacitors. Capacitors are useful in various applications, and when to use it depends on the scenario. We will be taking a look at some applications where capacitors can be really helpful. Such applications includes a filter capacitor, a bypass capacitor, and a decoupling capacitor. An example of a filter capacitor is a passive crossover circuits inside speakers, which separate a single audio signal into many. Another popular example of a filter capacitor is a low-pass filter circuit, where it allows low-frequency signals to pass through. In the case where we want high-frequency signals to pass through, we would then use a high-pass filter circuit, where the capacitor and resistor's positions are switched. In the case where we want to prevent noise from entering a system, we would then use a bypass capacitor to bypass the noise to the ground. The decoupling capacitor is used to isolate or decouple two different circuits. For instance, it is used for decoupling AC signals from DC signals or vice versa. The bypass capacitors and decoupling capacitors have many similarities and are used interchangeably. The only difference between the two is that the bypass capacitor are designed to shunt noise signals, whereas the decoupling capacitors are designed to smoothen the signal by stabilizing distorted signal. As of now, we know when capacitors can be useful and when to use it. Let us now take a look at how the capacitor works internally and how do we decide the right capacitance value to use. When current flows into a capacitor, the charges get stuck on the plates because they can't get past the insulating dielectric. Electrons, which are negatively charged particles, are sucked into one of the plates and it becomes overall negatively charged. The large mass of negative charges on one plate pushes away light charges on the other plate, making it positively charged. The positive and negative charges on each of these plates attract each other, because that's what opposite charges do. But with the dielectric sitting between them, as much as they want to come together, the charges will forever be stuck on a plate until they have somewhere else to go. The stationary charges on these plates create an electric field, which influence electric potential energy and voltage. When charges group together on a capacitor like this, the capacitor is storing electric energy, just as a battery might store chemical energy. This formula shows the relationship between charge, capacitance, and voltage. By knowing one of these two variables, you will be able to find the unknown variable. This is a conversion chart to easily help us convert between the various units such as pico and microfarad. Let us now take a look by using the formula as shown earlier on to calculate capacitance. Let us assume that we want 0.009 coulombs of charge and we have a voltage of 9 volts. By using the formula C equals to Q divided by V, we have Q as 0.009 coulombs and V as 9 volts. Applying this formula will give us a 1000 microfarad. In this case, we will need a 1000 microfarad capacitor. Just like resistors, capacitors can be connected in both parallel and series. To find the total capacitance of capacitors connected in parallel, we'll just sum up all the capacitance value. An example shown here will be given two capacitors connected in parallel with both 10 microfarads, we just add them up together, giving us a total of 20 microfarads. In the case where capacitors are connected in series, to find the total capacitance will be a bit more challenging. Therefore, taking an example of two capacitors in series, we'll then use this formula where C total equals to C1 multiplied by C2 divided by C1 plus C2. Let us now take a look at an example using the 10 microfarad capacitor again. Using this formula, we get the numerator of 10 multiplied by 10 and the denominator of 10 plus 10. That will give us 100 divided by 20, which will give us a total capacitance of 5 microfarad. Connecting capacitors in parallel will result in an increase in total capacitance, whereas connecting capacitors in series will reduce the total capacitance. To measure capacitance, let's first connect the capacitors in series. Take note of the polarity of the capacitors. Next, let's turn on the DMM. To measure your capacitor, you need to switch the symbol such that you see the word capital F. This is in the capacitor mode. Let's now measure the capacitance in series. As you can see, it is 62.96 microfarad. The capacitors that I have used here is a 100 microfarad capacitor, as you can see over here. So if I were to measure the capacitor alone, you will see 100 microfarad. So it is not exactly 100 microfarad in this case. There is an offset for this example. Let's now measure the capacitor in parallel. To do that, I will connect the capacitors in parallel. And now I will start measuring. As you can see, when the capacitors are connected in parallel, we get 129 microfarad, thereabout. This shows the effect of capacitors that are connected in series and in parallel. Let's now take a look at why we use capacitors. We use capacitors because it can hold small amount of charges to power up circuits, and we've seen some of these applications where capacitors can be really helpful. Now, let us take a look at a demonstration of a charging and discharging circuit by using a capacitor. Here, we will be showing you how a capacitor can be useful in a charging and discharging circuit. If you would like to follow along, please get ready the following components: 1 mini breadboard, 1 9V battery, 1 1000 microfarad capacitor, 1 LED of your choice, 3 1 kilo ohm resistors, 1 jumper wire, and 1 push button. This is the schematic of how you'll be connecting the capacitor in the charging and discharging circuit. As shown in this simulation, when the push button is pressed, the LED lights up. At the same time, it charges the capacitor. When the push button is released, the stored energy from the capacitor is being used to power up the LED for a short period of time. If capacitors are not used in this circuit, when the push button is pressed, the LED will still continue to light up. However, when the push button is being released, the LED will go off immediately. To follow along, please lay out the components as shown here. This is how the connected circuit will look like in real life. Now, let's get our hands dirty by following along with the tutorial to connect the components one by one. To get started, let us first get the jumper wire and connect it in the following order. Next, we will be using the push button. We'll connect it to the power supply. Thereafter, we will be getting the aluminum capacitor of 1000 microfarad connected in the following order. Do take note that the longer pins will have to be connected to the power supply, the shorter pins to the ground. Now, let us connect 3 of these 1 kilo ohm resistors in series to achieve a total resistance of 3 kilo ohms. Remember to bend the legs of the resistor properly before inserting it into the breadboard. Otherwise, you will be having issues making sure that the circuit is properly connected. Thereafter, we will be connecting the LED, where the longer pins again is connected to the power supply, shorter pins to the ground. Lastly, let's connect the power supply, where the red wire goes to the top with the positive side, and the black wire goes to the ground. Let's now take a look at the completed circuit and hold on to the push button. You can see that the LED is being powered up. At the same time, the capacitor is charging. This is the charging phase of the circuit. Holding longer allows the capacitor to build up charges. When we released, you can see that the LED slowly dims down. This is the discharging phase, where the charge from the capacitor is being released and used to power up the LED. Let us now take a look again. Holding on to the push button for a longer period of time will allow the capacitor to build up more charges. And you can see again that the LED did not go off instantly. Let us now take a look at the circuit when we remove the capacitor. When the push button is pressed, you can see the LED lights up. However, when we release the push button, immediately the LED goes off. This shows how a capacitor is useful in a typical circuit like this. To find out how long does it take to charge a capacitor, given a 3 kilo ohm resistor and a 1000 microfarad capacitor, we use the formula tau equals to RC, where tau is equals to the time constant, R and C are the resistors and the capacitor values respectively. Using 3 kilo ohms multiplied by 1000 microfarad, we get a time constant of 3 seconds. One time constant will allow capacitor to charge up to 63% of its capacity. For up to 99% of its capacity, we will need 5 time constant. Therefore, we will multiply 5 with 3 seconds, which will give us a final result of 15 seconds for us to fully charge a 1000 microfarad capacitor. You may be wondering, how will you be able to get your hands on a capacitor if you want to work on a project? You may purchase it from any electronics store that sell components or online via DigiKey, Mouser, Element 14 and RS components. Here, we have provided you a guide on how you can purchase the 1000 microfarad capacitor as used in the practical demonstration. We have now come to an end of this short video series. We hope that you have understood more about capacitors and find it useful to get you started in any electronics project that you may want to try out. Thank you and see you again.